the reason I go and talk about factor graph is that now I can visit the classic problem, sequence prediction. I have a sequence of observations. I have many observations, and then I want to infer something about these latent state. And this is a little bit similar to an HMM, okay? So this is like at every point in time, I have potential, and so I define a potential. I define potential between my latent variables, and a latent variable, if you remember, is maybe it's a binary, it's like 0 or 1, or it could be a discrete, like maybe 0, 1, 2, 3, 4, 5. So this is the H1. The same for H2 can be maybe from 0 to 5, 0 to 5. And then I have potential between them. I could decide to tie the weight. I could say the weights here are also tied to the weights here are also tied. So these weights could be tied or untied. And then I could say, but this latent variable is not just has like a dependence, it has a link. And I use the word dependency. And I know in an HMM, we're going to talk about probabilistic graphical models. When we talk about the Bayesian network, like this link here will be through a conditional probability that you define these. In the case of the Markov random field, the main difference is there's no restriction to have these to be probabilities, as long as they're like any value from like minus infinity to plus infinity, although you probably want to keep it in a smaller range for just numerical stability. But there's no constraint that these are probability. And that's why they're like, you should not see it as like H2 given H1, which is the way you would look at it from a HMM. No, here this is just like, this is a symmetric relationship, like how likely these two events co-occur at the same time. That's the simplest way to see what is the potential that these two events co-occur at the same time. That's the way to look at this. And the formulation looked like an HMM. I could have put my X here explicitly, and that's what it is. But the big difference is I don't define it as a conditional probability, the dependence. I will look at it as a symmetric. How are those two events to be co-occurring at the same time? How is that latent event to occur at the same time as an observed event? That's the way to think of those unary potential. How I have some observed event and maybe me smiling, and I want to have my H that is going to model all the different emotion maybe. And if you remember, like in the HMM, this latent variable is like 0, 1, 2, 3, 4, 5. It doesn't have a direct link to the label directly. Maybe this will be in fact predicting a sequence of happy. So the label will be more like you're going to have one model, maybe a Markov random field for happy, and then you have a Markov random field for sad, and then what so you'll have a set of parameters for the Markov random field for happy, and then a Markov random field for sad, and then I give you a video sequence, a bunch of video sequence, and then I see which one match better. I give you this and this input, and then which one match the better. And so I can look and find what is the probability, which one has the largest probability or likelihood in this case, not just probability, but likelihood. And that will be my way of using something like an HMM or a Markov random field for this. And so I know it's a little bit abstract, so I would like to revisit our example, but look at it from a Markov random field perspective. Like, how do I use this from a Markov random field how do I do it? And I will start doing it with a graphical model representation where only things can be pairwise connected. And so in that case, I will follow the same kind of thing as I will have for a Bayesian network. But the difference here, you have to look, because it's not directional, it's both ways. What it means is it's not like P of H give P of X given H, or it will be modeled with this kind of link here. But no, what I will model here is like, what is the potential of both, let's say learning is a binary, like learning is either high or low, high learning or low learning. What is the potential of a high learning and a high number of book that I viewed? And let's say number of book can also be binary, like high number of book that I viewed or low number of book I viewed, high number of nodes or low number of your nodes, high number of posters, low number of posters. So the potential is because it's a symmetric relation, is really looking at how these co-occur. How are these co-occurring for performance of high number of correct answer and high performance, or low correct number of answer and low performance. And similarly for the valence, I will start looking at a high learning, what's the probability, not probability, but potential of having an event of high learning and high valence or positive valence, and low learning and high positive valence. And then I can do positive balance and high performance, positive balance, and low performance. This is example of what will be modeled by each of these links. This is the graphical model, and then you can add to this all the different links that I previously had in the other. But a factor graph gives me more flexibility, and I like this a little bit better. And like, so if you look at all of this, like, where will it make sense to not just have a pairwise, but have like a meta node that will really take into consideration not just pairwise, like learning with valence, performance with valence, and then personality with valence, each of them separately. That's not really how the model was originally designed. Like, if you remember, like when we look at the theory of emotions, the theory of emotion, it was saying that it is jointly, that like maybe I have praise and my personality together. And so like, instead of having these separately, which will be the simple way of putting factor graph, is like keep exactly the same link and make it as a factor graph representation. And if you look at this model, like how many of them are pairwise potential and unary potential? How many unary and pairwise? Pairwise are between two random variables. So you have 1, 2, 3, and 4 pairwise potential, and unary are between random variable, latent, and then with observed variable, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11. So, but how to improve the factor graph? As I mentioned, this is a nice way. What I like of this representation, now it makes a lot more sense to me, because the decision of valence is not just pairwise, it's maybe a contrast between learning and performance. It's like high learning, high performance, or high learning and low performance. That's the contrast between these two that is really useful. And if I just do pairwise, this will not be explicitly modeled. But now I have a way of defining a potential function that could model that contrast really more easily. And I could have contrast also between my valence and my personality to focus. That is another way I could better represent that. So if you ask me, this is a better way of representing that model, taking into consideration. So this is an example of building a factor graph and Markov random field. But these models these are generative model, in fact. Markov random field, the basic Markov random field, in fact, is designed to optimize P of y given x, P of y, the emotion, no, not P of y given x, I said generative. So P of x and comma x, P of y, comma x. So P of emotion and these events. So that's a generative model. But I would like maybe, and may want to not model the joint distribution, but I may also want to model the conditional random, the discriminative. Maybe I would like to have a discriminative random field. And that's what the conditional random field does. It says, okay, now I'm not going to model P of A, Y, and X. I'm going to model P of Y given X. And so that's the main difference of the conditional random field. The rest of the formulation is a lot like a normal Markov random field. I will define that probability, P of Y given X, using potential function, which are defined with both pairwise potential and unary potentials. And so that tells me, and maybe I have one X for the whole sequence, or it could be many X, one X for each of the time sample. And then finally, one thing that I will do in a typical conditional random field is I will often tie the weights. So the weights for these will often be tied with this, like the same way. And that will allow me, if I don't do that and I don't tie the weight, then I will need to have a set length for my conditional random field. If I tie the weights, then it allows me to nicely have it so that I can have any sequence length, because then these potential function is exactly the same as this. The parameters are the same on both. So this is what the conditional random field, the typical one, is like. It says where you have one potential function, maybe for defining the relationship between X and Y, and then you will have a unary, and you will have tied the weights between each of the pairwise and each of the unary. And when the conditional random field was introduced, instead of calling them potential function, or calling them energy function, they decouple it and they just call it feature function, but it's just another name convention, unfortunately, that got so now potential function, energy function, feature function, they're almost the same up to some exponential of each other. So just unfortunately there's the naming convention. And how do you optimize? What's really nice with this is that this has a nice gradient that can be computed analytically. You can compute this. I did it myself during my own PhD. And you can compute it specifically. You can optimize inference. You can gradient if there is no loop. If it's loopy, then that's going to get a little bit more challenging. But if it's a chain, or if it's a tree, then the inference can be done. And often the inference can be done with belief propagation, or like a forward-backward kind of algorithm. And so one of the first application of this was, in fact, in text. And I will, if you ask me, these are wonderful for text. And these were, in fact, that's a 2003 paper, I think. If you remember, back in the days, the text was also represented as a one-hot encoding. So it's a 10,000 length. That's what this often were done. Now these days you will do word embedding and all this. But why is it so cool that the when you have a one-hot encoding, is that X is going to be a bunch of 0 and 1, and maybe your label is like also 0 and 1, like is it like happy, sad, or is it a determinant, or is it the beginning of a noun phrase? Like so if you have y bunch multivariate but like bunch of 0 and 1, and the same for the x, what's really nice with this is then the potential function are really intuitive, because they're just like, hey, are these two events just high potential of co-occurring at the same time? Is that word very high potential of co-occurring with that label? That's what this model is going to tell you. Now, if you start using like a word embedding where it's no more just 0 and 1, but a continuous value, then the potential function will have two tasks at that point. One is to know, is these two events likely to happen, but also it will need to kind of normalize your feature to be in the same kind of range as the others. You could do it yourself and help the model, but if you don't, then this is going to have the parameter associated with it will have to normalize it for you. And that's why when you have binary output, very 0 and 1, and the output of a neuron, if you make them very sharp, like they're almost 0 or 1, like if depending which activation function you have. So it makes sense that you could use the output of a neural network, depending on what you may want to tweak, which kind of activation function you use right before the CIF, just to make it a little bit easier for the CIF. So for the task of the shallow parsing, it is like detecting the noun phrases, like beginning of a noun phrase or continuation of a noun phrase. So I ask you, if there's 3 labels, like beginning of a noun phrase, continuation of a noun phrase, or others, there's 3 labels. How many parameters here between, then let's say my vocabulary is 10,000. I have 10,000 and I have 3 labels. How many parameters here do I have? Okay, it will be 3 times 10,000, so 30,000. And what does it learn is how likely that word co-occur or happen, potential that this co-occur with the beginning. That's what this is going to learn. And what the E is going to learn is going to be a transition. What is it? How likely that what's the potential that if I have a beginning that I will have no continuation, and one thing is like, if I have a beginning, how likely that I have a continuation? And so this is what you will get from the from these potentials. But in many cases, you don't want to just model directly observe to the label. You would like to have something in the middle. You'd like to have some latent process. And the latent dynamic CIF is a nice little extension of that. And in this case, is like if you would like to do something like do prediction of noun phrases, it will be a very easy task if someone had manually annotated the part of speech tag. Because once you get the part of speech tags of the word, it is almost a straightforward task to do. But there's this like latent, and you don't want to manually annotate it, so you're gonna just put it as a latent variable, like, and you're gonna, maybe the number of state here may be similar to the number of known part of speech tag for that language. And so, and what you will do is you will say, you will have some hidden state associated for the beginning of a noun phrase. You will have some hidden state associated with the others, and then some of them for continuation. And then we can nicely, if you do this assumption, which is an interesting assumption, is you say, for each of my label, I will have a subset of hidden state. If you do that, then the latent dynamic CIF end up being mostly the same equation as the CIF, but with a different kind of summation. And that summation just correctly assign hidden state to their label. That's what it does in the CRF. And so with the LDCRF, how many parameters here? If I have 10,000 and I have 12 of them, so it will be 12 times 10,000. And what does it learn? Here is a kind of a clustering. It's a clustering that happened. It's a little bit like the HMM. Latent variable are often, you should see them as clustering. What it does, it takes those 10,000 words and cluster them in 12 different bins. 4 of these bins, if you cluster anything in 4 of these bins, it's going to be supposed that it is related to the beginning of a noun phrase. If you cluster any of those 10,000 words in the middle ones, then we'll suppose it's a continuation. And if you cluster a word in the last 4, then we'll suppose that it is the other one. And so that's what you will learn here. It's kind of a clustering with the theta X. The theta E is interesting because it's going to learn 2 different things. It's going to learn what's called intra-class dynamic and between class or cross-class dynamic. It will learn within a class, like within like all of these beginning of a noun phrase. Like, what is the probability to go from B1 to B2? What's the, not probability, but what's the potential to have both B1 and B2 co-occurring at the same time with these values? What's those co-occurrence or potential of B2 and B3 to co-occur? That's the intrinsic dynamic. The more interesting is extrinsic, what it is from B1 and co-occurring with I1 like at the next time step. That's extrinsic dynamic. And that's really interesting because now your model, your hidden dynamics here is going to model both within the label and between labels as well. And when you do it in real data and you learn a model with this, and then you look at these predicted hidden states, it's really interesting because you see that effectively the text ended up being clustering. You never told that B1 should be about specific part of speech tag, but what's really interesting is that it naturally cluster it for you. So B1 ended up being a lot more determinant pronouns, and that's the beginning of a noun phrase. The house or the greenhouse, very likely to have a determinant of a pronoun as the beginning of a noun phrase. So it not only learned that determinant and pronouns are likely, but it put them in 2 different bins, 2 different latent states. So this is a latent dynamic conditional random field. And another one that's and that's one of the last one in the family of conditional random field before we get into the multimodal. But it's the idea of having only one label. What if I have only one label? I have all these words and I want to know the sentiment over the whole sentence. Then the hidden conditional random field allow you to do it. What it will have potential between the hidden state. It will have potential between the observed and the hidden states. That's the same. And then you have also the potential, and these will be shared between labels as well. And so the inference is tractable in linear sequence. And so you can train that using gradient descent. If you want to train the usual way, you will use more of a Newton-based approach. And instead of using stochastic gradient descent with batches, you may use all of the data. But this is non-multimodal. But what if you have multimodal data? And let's say that my input is both language and visual. There you can learn, you have a model and you can make it multi-view. What it means is your audio is going to have its own hidden dynamic, and then visual will have its own hidden dynamic. And then you need to pair it, the two of them. And one way to do it is to directly, or you could also do a coupling. But nicely, this model, what's really nice is that it allows the problem with doing the same as if you remember with the HMM is we had to couple. We had to couple temporally coupling things. Here we don't need. The model allows us, because it's modeling those potential functions, allows us to directly model the co-occurrence, like potential of events happening at the same time, synchronously. And that's what's called a multi-view HCIF model, where your probability of Y, that's what you want to model, probability of Y, given your XA and XV and your trained parameter theta. And then the idea is to solve this simply by integrating over all the hidden state. And now this can be done. There's nice ways to approximate this using loopy belief. If you realize the problem here is that you suddenly have loops, and so you have either junction tree or loopy belief to do that. One of the advantages of the CIF is that I can not only model with conditional random field, but I can also bring neural representations with it. And so I can go ahead and take my representation, my input representation, and use neural network, and then on top of a CIF. And if you ask me, if you have CIF and neural networks and you want to merge them together, it makes a lot more sense to have neural networks at the bottom with where you have a high dimensional. And so we've seen beautiful work on like learning good representation, and maybe you pre-train that representation with another data set. And then the conditional random field allows me to put knowledge that I have over the structure of my label. And here, the knowledge I have is that it's a sequence, it's a temporal information. And so I will put that knowledge of temporal contingency in my model. And so the conditional neural field, what it will do, it will model my, my temporal consistency, and it will also model here my grouping. So what does this do? If you remember, it's a lot about clustering. It takes some high dimensional, embed it into some lower dimensional, and then take this and kind of cluster it into these different labels. That's what it's gonna do in this. And so this is the this function here will be defined based on the neural network. And here, this could be as complex as you want. I mean, I put it only one layer, but it could be as many layers as you want. So this could be as many neural networks layers as you want. There's nothing stopping you from that. And now, as you can expect, people decided, hey, why are my representations not recurrent? And yes, you can do it. There's nothing stopping you from just going and saying, hey, I'm going to learn a representation for X that is contingent. So that's what the LSTM, but the LSTM is always, you always should think it more on the representation learning side. But I may have some knowledge that in that task, there is two things that's useful with the CIF. One is that my state has a nice discrete clustering that I want to take advantage of. And the second is that there is a structure, and here is a simple temporal structure, could be a little bit more complex, But and the nice thing is you can go and back propagate. The learning is feed forward, and then the gradient back propagation. So here you will do belief propagation for that part, and then back propagation at the same. So feed forward, belief propagation, and then back propagation. So what will be the number of parameters in this? So theta E will be based on the number of labels. So if you have 100 entities, so it will be 100 times 100. And as I just mentioned, what do you get from the LSTM? A lot of it is, in fact, from what you get from the LSTM is a little bit of a recurrence of your representation, but it's still in the representation learning phase. Here, what I get is I can integrate knowledge over my labels. And finally, you could go all the way, put everything in, and just say, hey, not only I want deep neural representation, LSTM, and also CIF. So there was this paper that brought everything together. And one example would be character embedding for that. I talked and gave an example at some point where I would like maybe to not just have my direct link with my direct neighbors. Maybe I want to do also continuous prediction. And so maybe my prediction here are not just discrete, but I want to predict something over time that is also continuous. And so in this case, the equation is really similar as a typical conditional random field. The problem is here is that I need to, like a conditional random field, I need to divide by the potential function, and the partition function, sorry. And this partition function, in the case of a CIF, we had some little tricks to make it work because they were discrete states. But if it's continuous, you get that very infinite integral that you need to integrate over. That gets a little bit harder. And so for that, when you see this kind of like infinite, one thing you should think about this kind is to think about it right away as a multivariate Gaussian integral. That's usually a good trick. If I can take this equation and put it as a multivariate Gaussian integral, if I can make it in that form, then I have a closed form solution. What it means is that now I can't use any potential function or any feature function. They need to be feature function that will allow me to eventually have a formulation that is close to the multivariate Gaussian integral. And so this is one example that was suggested when this continuous CIF was presented. And so you can take this and because it's closed form, what's really nice is that it takes this the CIF conditional probability that you're modeling, and then now suddenly you don't need to go gradient descent, and now there's a closed form solution. So it's beautiful. And then that one is related to the matrix of here, and then one is related to this. And so since CNF can be viewed as a multivariate, then the optimal of a Gaussian, like since it can be seen as a multivariate Gaussian, then what's the optimal of a Gaussian distribution? The prediction is simply the mean of it, and you can optimize. So yeah, and then what's really nice is like, as long as I can keep it into the multivariate Gaussian distribution, then earlier I mentioned that closed form solution is closed form solution for the inference of the probability. I will still need to do at optimization time do a gradient descent. Sorry for this typo. But the closed form solution is for the inference. So I can really quickly get the optimal Y. The high order allows you if we use certain potential function to connect anything with anything. And finally, you get to the fully connected CRF. And that's, as you remember, that was one of the examples I gave you. I said fully connected CRF is very interesting because now every pixel will be connected with every pixel, or at least I'm going to be connected with all of my neighboring pixels. And the challenge there is that to do the inference, it can get a little bit hard. And so what I will do is, in fact, look at it as a mixture of kernel. And if I do the optimization for this, I often end up doing this with an approximation using the mean field approximation. And we'll discuss a little bit the mean field approximation when we discuss next lecture, when we discuss a variational autoencoder. But yeah, mean field approximation. So it's not exact, but by doing this approximation, then I can get my, in one shot, I can get all of my prediction. And I can use, and that's one of the paper that is presented for today, and that's going to be my last slide today, is that I can use this idea of fully connected CRF to predict the action of every frame in the sequence at the same time, and not only allow for first order Markov assumption, but allow for every frame to be connected with all the other frames. And that's another example of bringing CRF with neural representation. If you look at the slides that are posted online, you can see a few examples of another example where the labeling of the CRF is not a hard labeling, but a soft labeling. And that's what's called a soft label chain. I invite you to look at the paper for more details. Okay, thank you very much for your attention.